I thought this laser fusion thing sounded cool. I actually worked out at Princeton on tokamaks for a little bit. So if anyone wants to talk about magnets later, I can. But I'm going to focus on what we do at the LLE today with Laboratory for Laser Energetics, because it's actually pretty rare to talk about laser fusion, but it's got a lot of funding, and we've arguably made the most progress on fusion, period. All right, so this is the facility. It's in upstate New York. So if anyone ever makes your way up here, feel free to hit me up and I'll show you some very large lasers. This bay right here is one of them, and this bay over here is the other laser. They're actually interlinked, which is a really cool thing that we can do. And then this is just another picture of one of our experiments. And then I have to thank all of my collaborators. I stole these slides from everyone else's presentations and rammed them all together into one final presentation. So we'll start out with what is nuclear fusion, just in case no one knows what I'm talking about. We'll get into ICF, a little bit of history of it, and then specifically talk about the National Ignition Facility, which is the largest ICF facility in the world over in Lawrence Livermore National Labs. And we'll talk a bit about the future. So we all know fission, know and love it. Neutrons come in, split heavy nuclei, make lots and lots of clean power. And the neat part with fission is that it's really easy to do. We all know there's some political concerns. The fuel is relatively rare compared to fusion fuel, not actually rare, but you know, if you're gonna compare these two sources, it's worth pointing out that fusion uses incredibly common stuff like deuterium. There's plenty of deuterium in my coffee mug right here. I think it's something like enough to power Rochester for a day or something like that in the deuterium in my coffee mug. The easiest fusion reaction, and the one that we primarily focus on, and this is easy in big scare quotes, is deuterium-tritium. So deuterium is a heavy version of hydrogen. It's in the infamous CANDU reactors that are just north of me. Tritium is a radioactive form of hydrogen, and these two have the easiest way of making fusion. Now, tritium has a 12-year half-life, so we have to constantly make tritium. And this reaction is what powers the largest nuclear weapons as well. So there is actually a big supply of tritium out there. Primarily from the CANDUs of all weird places. We get almost all of our tritium shipped over from Canada. There are ways to breed more tritium in reactor designs, because you'll notice we get helium-4 and a neutron, and one screaming fast neutron. If you know anything about fission neutrons, they come out about 1 to 2 MeV, and then they slow down to quote unquote room temperature, thermal neutrons for most reactors. And that means they're not super damaging to materials. Fission or fusion neutrons, specifically DT neutrons, are 14.1 MeV, which means when they hit something, they can often make more neutrons, which can be a problem. We also get significantly more neutrons per unit of energy. If you just look at the math here, there's about 200 MeV coming out of fission and 17.6 MeV coming out of fusion. Get, say, 2.5 neutrons per fission reaction. We get 1 neutron per fusion reaction. You normalize that out, fusion's a lot nastier neutron-wise. But there's a lot of interest in pushing towards fusion for all sorts of reasons. I'm sure we're all nuclear fans. We know why people are interested in fusion. So to start out with, fusion already works. Thermonuclear weapons, our largest nuclear weapons, can derive something like 95+% of their energy from fusion. And of course, stars, although stars use a very different reaction than what weapons do. The trick, of course, is we'd like to make it in a controlled manner in a laboratory at small scale. 50 megatons at a time is not very useful for powering a city. We'd kind of like it to come out more, say, at a gigajoule per second.
Did they try that though? The PACER project?
Project PACER, they looked into this. It would work technically. The economics, even without the political considerations of having to make 100 nuclear weapons per day, are quite questionable, as you can imagine. It's one of the few times where scaling up doesn't help you because it's too big. They were talking about something like half of the US grid coming from one power plant. So what happens if we need to do maintenance?
just for everybody who hasn't heard of this, this is the underground detonation of nuclear weapons and then harnessing that energy to make electricity.
As Edward Teller, the father of the hydrogen bomb, would like to joke, and also the father of laser fusion, Project Pacer is the only way we know to make fusion power that definitely will work. So the trick with fusion and why it's so hard is we have to contain matter at unbelievably extreme conditions. We're getting into the realm of plasma. So, you know, solid gas, liquid, or solid liquid gas. Plasma is even beyond gas in terms of temperature. So at 10,000 degrees Kelvin, like the temperature of the hottest welding flame you've ever seen, you're just barely getting into plasma. We have to go millions of times higher, or at least hundreds of thousands of times higher to get to the fusion regime. And the reason for that is, if you look at these two hydrogen nuclei here, I'm trying to make those come together to get energy. Well, they're charged. And it's just like if you had two magnets of the same polarity, you try to force them together, they really don't want to force together. So we need to get them going very fast, and high speed random motion is the physics definition of temperature. So we have to get them very, very, very hot. And there's kind of a range here between pressure and time and temperature to try to get fusion that we'll get into in a second. But the really important part is there is no material structure that can contain fusion plasma, period. We cannot make fuel rods. We cannot make pressure vessels. We can't do anything like that. So we have to get very, very tricky because we are way above where things melt. The toughest materials out there melt at under 5,000 Kelvin. And like I said, we got to go way above it. So the two big kind of thrusts towards fusion, there is magnetic confinement, as shown over here by ITER, which is the gigantic tokamak project in France that they're working on. And there's inertial confinement, which is shown here by NIF, which is the National Ignition Facility, already built and operating in Lawrence Livermore National Labs. It was turned on, I believe, in 2010. And this is primarily what we're going to focus on. But like I said, there with fusion, you can imagine you want to get things going fast, and you want to get those fast things very close together, and you want to hold them for a very long time because you're trying to get a lot of reactions to happen at once. So we call this the Lawson criterion. And if you normalize all those numbers out, it comes out to just 10 atmosphere seconds. And you think, wow, that's really easy, but it's 10 atmosphere seconds at, 100 million degrees, which all of a sudden makes it much, much, much harder. So for magnetic confinement, they go for very low densities. This Ni number, this is the number of ions per cubic centimeter. That is way lower than air in terms of just like number of atoms per cubic centimeter in air. It's something like 10 to the 17. This is 10 to the 14. So we call these sorts of reactors hot vacuum, basically. And then you want to hold it for a very long time because the density is low and you have to drive the temperatures up. For inertial confinement, we go the other direction. We say, what if we just drive the density super, super high and we just let it explode? Think just like how your car engine works. You compress the fuel, goes off, boom, boom, and keep retrying. That's the broad idea of inertial confinement. And so we go for these sorts of ion densities, extremely short time scales, billionths of a second, and at densities equivalent or more than lead. Either way, very extreme facilities, as you can imagine. So a couple quick definitions that we need to go over with fusion, because people like to throw a lot of stuff out there, and it's important to know what we're actually talking about. A big goal is burning plasma. So this is when a fusion chain reaction actually begins to self-heat. So just like how a fission chain reaction can sustain itself, with fusion, if we go back here, these alpha particles that come out of the fusion reaction can go on and heat up more fusion fuel. So that's how a nuclear weapon gets that massive release of energy with that huge chain reaction from a relatively small input from the initial fission weapon that's used to trigger it. You'll have a 1 kiloton fission weapon that will trigger a 50 megaton fusion weapon. It's not just fission powering it the whole way through. So you have to have a chain reaction. And burning plasma, that burning plasma chain reaction is what ITER is hoping to accomplish. NIF pulled this off in 2020. It's 10 years late. They were supposed to have done it in 2010, but they did pull off a burning plasma in an inertially confined fusion pellet in 2020. Ignition is when the fusion chain reaction is fully self-sustaining. So it just and it will actually run away. The way you design a fusion reaction, chain reaction, is to run away. Very, very unlike a fission chain reaction, because it will eventually get so hot that it will radiate too much of its heat out, and then it will stabilize. We must get ignition for fusion to be a practical energy source. It's the only way to get enough what we call gain, energy out versus energy in, to actually make usable amounts of energy. Excitingly enough, NIF did this in August of 2021. They achieved a gain of 6 on the first ignited fusion pellet ever. It's the first time this has ever been done without, the power of a nuclear weapon to do it. They have not been able to replicate that trick, but it's important to keep in mind that NIF can only shoot once every day, and these fusion shots are very costly and rare. It does a lot of other science. They're working on it, and they were probably right on the edge, because it wasn't a very exciting gain. The initial claims for NIF were they were going to get a gain of, like a gigajoule out, and they got something like 1.6 megajoules. But still, they did it, and that's very exciting. Break even.
These like just very, very short instances.
Yeah, it's an explosion when it comes to NIF specifically, or any sort of pulse fusion mechanism. It's all about releasing all of this energy in a very short period of time, just like how your car engine burns fuel, or more like how a diesel burns fuel. You compress it up to those conditions, it explodes, and then it's done. And then you feed in more fuel and repeat. Break even is when we'll produce more energy, more equal or more energy than when was used to totally create the reaction. Now, ignition is not required for this technically, but you will never get enough energy gain to make it worth it. No one has pulled this off yet, partially because no one's made a reactor to really try and do it. Ignition was seen as such, ignition and burning plasma were seen as such difficult things to go after. The next step would be break even, but you have to make an efficient engineered facility for it. Both NIF and ITER can never hit break even. They consume too much electricity in all of the equipment going on. They're not meant to have the sort of operating conditions to really do it. They're science machines. They're not power reactors. To ever compete on the actual energy scale, you have to hit break even, and you have to go way above break even. You don't want to build a 1 gigawatt steam turbine to get 10 megawatts of electricity out onto the grid because you have such a terrible gain. That is, you laugh, Eric, but there are designs that are not far from that. And it's why fusion has to meet some very serious conditions to ever be usable. These terms are confused all of the time. People throw them around for different things in fusion. It's important to try to keep that in your head when you see fusion discussions.
It seems like most of the articles you see, they're quoting like how long the reaction was sustained, and that's like the bragging rights. And I'm always thinking like, well, was it actually energy positive, or what?
Yeah, and the length thing, you see that all the time for tokamaks. They talk about how long can they pulse it. They're almost never hot enough to matter. You'll often, if you know anything about tokamaks and you dig into it, what you end up finding out is that either the plasma is too cold, or the plasma is not dense enough. And so the output isn't that impressive. You're like, great, that's awesome. It's like you revved up your car in your driveway and said, because of that, I can now drive to New York. Not really.
Is that them just trying to like get more funding? Oh
yeah, that's a huge game in fusion, specifically the magnetic people, because as you can imagine, in the inertial world, we have a different source of funding that's much more reliable, namely the United States military. Yes. So there's 3 common approaches to inertial confinement. There's laser indirect drive, and I should say this can also be done without lasers. There's also particle beam direct and indirect drive, but no one has a particle beam facility, so we'll talk about laser. There's laser indirect drive. That is NIF. We can also do it at the place that I'm at, which is the Laboratory for Laser Energetics. Our laser is called Omega. However, we're not optimized for it. So in this case, the laser beams come in, they hit this gold container called a hull realm. The hull realm glows in X-rays, and then the X-rays ablate and compress the internal fuel. And we'll talk about that a little bit more in a second. That is how nuclear weapons do it. And that is why NIF was built the way it was built. Hull realms are the trick inside of a nuke. Laser direct drive is how you would imagine if I told you you're going to use lasers to make fusion. This is how you'd probably imagine you'd do it. You bring a bunch of lasers in, they hit the outside of the pellet, they burn off the pellet, and it compresses inwards. The lab I'm at is the lead lab in the world for this. We have the largest direct drive facility with the highest gains of anyone that's ever pulled it off. There's also a smaller Navy facility at NRL called Nike, but Omega is the primary laser. And then there are pulsed power magnetized fusion approaches, primarily led by Sandia with their Z machine. And this involves just dumping unbelievable amounts of current through a little tiny target. They've also had a lot of really good gains recently. All three of these have, the past probably 5 years, have had just incredible leaps that I don't think anyone thought was going to happen. If you got into this game in 2015, you would assume this whole field was going to die. But in 2022, we have all the records over the magnetic folks. So a little bit more into indirect drive. This is a NIF gold hull realm. They are very expensive. They are custom made by General Atomics. And like I said before, the primary point of this is not energy, it's stockpile stewardship, but the fact that we can use it for energy and other high energy density physics research. So like we can generate conditions inside of this little hole realm similar to the center of the sun. So we can study stellar physics. They've generated white dwarf conditions, like all sorts of wild stuff inside of these things. It's quite the science factory.
What's a hole realm?
That is what we call this little gold tube. It is a German word. I think it's something related to oven, but it's basically just something for the lasers to hit to then get super, super hot. So if you know how like you get metal red hot, and then if you keep going, you can go white hot. This gold thing gets X-ray hot.
Huh.
So it's pretty extreme. The reason they like it is, sorry, what'd you say?
Is it made out of gold? Is that what it says?
Solid gold.
Huh. It doesn't
They also do uranium for obvious weapons related stuff. And then there's been a lot of experiments with lead for a cheaper alternative. But when the US military is footing the bill, you will just use gold.
Gold has a pretty low melting point though, right?
Yeah, nothing in this picture survives. This entire thing is exploded into not just, fragments, but it actually becomes pure plasma and coats the walls.
Okay.
Wow.
Why do they use gold?
It has superior X-ray properties. And then if you ask any more, you either have to have a clearance or you're told to shut up.
All right.
Yeah, I would tell you if I knew. I do not know. This is not something I work on. Well, I would tell you if I knew, and I could tell you, I should say. So laser direct drive, this is Omega. This is our laser here in Rochester. This is another fusion explosion. You can see all the things we point in to study it too. Lots of diagnostics on sticks. And there are 60 laser beams coming in. You can actually see one of them right here where my mouse is. It's reflecting a little bit off the plasma, and you can see how that beam focuses in. There's 60 of those monsters coming in and compressing this pellet. And the same physics is at play in both of these. The outside of the pellet is ablated off, either by the lasers or in the previous case, the X-rays. And then it's just like a rocket. You imagine all that ablated stuff comes flying off, and it's flying off way faster than rocket exhaust. Your typical rocket exhaust is maybe 5 kilometers per second. We can make things fly off at 400 kilometers per second with the laser. So that pellet comes flying in at something like 0.05% the speed of light and slams together, generating incredible pressures and temperatures. But like Matt brought up before, a tiny period of time.
Does that pellet, is it just disintegrated in an instant?
It is turned into plasma. It undergoes thermonuclear reactions, and then it gets scattered to the wind.
How big is that pellet?
It is the size of a period at the end of a sentence.
Okay.
They are so hilariously small. They have so little fusion fuel in them, but the might of the atom, the amount of energy you can actually get out of it is stunning. Even Omega so Omega is too small of a laser to get true ignition. It was never meant to do it. It was just meant to study inertial confinement fusion. we've gotten a bit over a kilojoule of energy out of our little tiny pellet. So it's a kilojoule coming out of something like 1 milligram of fuel. It's a pretty impressive result.
How do they capture the energy?
Right now, no fusion project in the entire world captures the energy. The long-term plan for ICF, and I have some slides on this at the end, is because we don't have to have magnets or anything nearby. The actual chamber is just a big old chunk of aluminum, and later it could maybe be steel or something else. We would just let the chamber get hot because the lasers, as you can imagine, can be very far away. And then we bounce them in with mirrors, and they can fire very fast. They've fired lasers of this scale faster than once per second. So you would fire in fuel, blow it up, and you would just heat up the wall, boil water or sodium or helium or whatever working fluid you want, spin a turbine, and you're off to the races. Of course, that sidesteps the entire difficulty of you have to make one of these targets every second. You have to have this incredible laser. There's a lot. It's not like fission where you just take the magic rocks, put them in the water, and it boils the water, and you're good. Mm-hmm. The real trick with laser direct drive, by the way, which for a while we thought was never going to work, is smooth lasers. And the lab that I'm at has done a lot of work to make better lasers. We actually we had someone get the Nobel Prize back in 2018 on laser work. We do a lot of R&D to make better lasers that impact all sorts of things. Like, for instance, if you've gotten laser eye surgery, you can thank LLE laser physicist, not me. I don't do that, but LLE laser physicist helped make that happen. And then here's the pulse power approach. This is the Z machine, big, glorious bank of capacitors. I actually know the guy who designed this machine. He hates this picture. He cringes every time he sees it. This is the Z machine breaking, which will take 3 or 4 days to fix because it's getting arcs inside of places it's not supposed to get arcs. But it ends up putting mega amps of current through fuel, and this is a nice little simulation, and then it ends up compressing the fuel. It just squishes it really, really hard with the magnetic force. And they've done some good work combining this with lasers to get heating and et cetera, et cetera. It's an exciting potential way forward just because of the inherent efficiency of this sort of system. The wall plug power, so to speak, is much better than lasers, but it also hates existing. And so the machine likes to break. If you know anyone who works at Sandia, they'll tell you that when Z fires once per day, and when Z fires, it will break the windows in your office and your car alarm will go off and all sorts of terrible things can happen depending on where you're sitting. So you can imagine that this is definitely not something that's going to fit into a Star Trek spaceship very easily. So just a little bit of history, and then we'll kick on through. This is one of the original ICF lasers built by Livermore, and this just gives you a little bit of idea of the size of these things. They're very big and long. This is the predecessor to NIF called Nova. We started out with just little baby lasers, and at 100 joules. And that's not actually baby size, but it's baby for ICF. And interestingly enough, there was a private company that did laser fusion first because they thought it was going to be so easy. The initial calculations from John Knuckles and Edward Teller said, "Oh my goodness, we're gonna build these lasers in the next couple of years, and they will immediately ignite fusion, and that's what's going to power the world." And so this company got funding, they got tritium, they ticked off the Department of Energy to no end because it's nuclear weapons related, and they did the first laser fusion, and it did not ignite, and it did not. They found a lot of problems and lost a lot of money. But it's really fun because the laser was invented in like 1961, and by 1970 they were trying laser fusion because it looked so promising. They kept upping the energy. And one of the things we discovered, most of these lasers make infrared light. And we found out that that's really, really bad. And no one really knew how to get around that. They made infrared light, and they have this sort of messy wave front to the beam. And we need to figure out ways around that. Anyways, they were able to invent ways to smooth the beam and get shorter wavelengths. So now all of our lasers are ultraviolet instead of infrared. And they just kept putting lots and lots and lots of money in it. Well, in the 80s, Livermore started pitching, and this is Ray Gun Ronnie's era. There's lots of money going out for all sorts of Star Wars things. And they pitched they're going to build this 10 megajoule laser. They're going to build it for $250 million, and it's going to get a target gain of 100. It's going to be the predecessor to how we're going to build a fusion power plant. And that doesn't get funded. But the interesting thing is the Soviet Union falls, and we decide that we're going to stop testing nuclear weapons. And so originally this 10 megajoule facility was canceled, but there was a lot of interest in keeping our ability to have weapons physicists and better understand our weapons without testing nukes. And so they said, let's build this laser fusion facility just for science reasons and just for stockpile stewardship. And rather than the 10 megajoules they wanted, they kind of needled them down to 2 megajoules. But an important little caveat to this is there was also a classified and now partially declassified test where they used at least two nuclear weapons far away underground as X-ray sources to then drive a big ball of deuterium, pure deuterium tritium ice. And that was their argument for this 10 megajoule laser facility, is they did some scalings and, typical physicist stuff. But, this is the sort of wild things they did back in the day in Nevada. It's called the Halite Centurion test. And so this entire field is based on a classified result, which makes it very weird because the guys like me, I don't have a Q clearance. I don't actually know the results of that test. I can't read it. I just have to take people's word that it worked. Of course, now that NIF is working better, I trust them, but for a while we didn't think it would. This is the National Ignition Facility, 2 megajoules, 500 terawatt laser, 192 beams, cost about $3.5 billion. Sounds like a lot, but for comparison, ITER is going over 30 billion and is not finished. So I would say it was a pretty good investment. And here's just a picture of the laser bay. You can see it's just a monstrous facility. And as you can imagine, being near the Bay Area, it is not cheap to get land. So I don't think they'll be building another one.
So so back to that picture, is all from building the laser?
As just the laser.
And what is all that piping? Like,
that is laser. That is where the beams go, where the amplifiers are, cooling. It's got 192 separate beams, and every single one of them has to be piped, and they don't pipe it through the air because they don't want to lose laser energy in the air.
Oh,
it is a serious feat of engineering.
Is that one long pipe that makes with a bunch of turns, or is that like numerous?
Each one is its own individual beam.
Okay.
There are 192 of these pipes.
Got it.
They're just not all in this picture because NIF has 2 banks of lasers from either side. So this is only one half of the laser banks. It's big. This picture does not do it justice.
Mm-hmm.
Do they use like mirrors or something to then angle them in different ways?
Mirrors as big as you, because we need to keep the intensity low. So you have to spread the beam out. Otherwise the beam will blow through the mirror.
Wow.
So the facility it's large in a weird way because not a lot of the stuff is very heavy, but there's just a lot of big weird things hung around that are very expensive because they're all optical grade. And this is, to this day, this is still the most energetic laser ever made. They started building it in 92 or maybe 93 is when they officially started, broke ground on it. And a lot of the technology, weirdly enough, actually came from the Soviet Union. When the Soviet Union fell, they just started snapping up laser scientists and discovered that there was things we didn't know. So like all of the amplifier glass in this, we didn't know how to make it until we got some nice Russians who showed us how to make it. So there's some other facilities around the world. LMJ in France, still under construction, will be equivalent size to NIF, and it's very similar design. There's a Chinese facility we're not sure about. This here is Omega, here in Rochester, and then Russia is claiming to be building a 3 megajoule facility. Don't know, hard to get accurate information. And one important thing to keep in mind with NIF, because I've been saying so many good things about it, NIF committed a mortal sin, which is overhype. And when they were building this, they went on very simple models. And this is a mortal sin that just about everyone in fusion has done at one point or another. But they used these simple models and said, our laser is going to do so good, it's going to hit 80 megajoules of yield is what we're going to get out of it. It's going to be incredible. We're going to put 2 megajoules of laser in. We're going to get 80 megajoules of fusion out. And you know what, as we get better, we'll probably go up to 200, maybe 300 megajoules of fusion yield. And they were telling Congress this, it's going to be easy. First shot, they brought reporters in for the very first shot of the laser. And their very first shot, they got less fusion energy than the little 30 kilojoule laser at my facility makes. They didn't even set off the neutron detectors. We've finally gotten up to 2 megajoules in, and now we're about 2 megajoules out, but we're still nowhere near these incredible claims from before. And this is, I guess this is my little way of saying, don't trust fusion people when they show you simple plots. Nature is mean and seems to always come up with new fun ways for fusion to get harder. But we did finally make progress. Here's a plot of yields. So here's that very first day when they brought in all those reporters, and the director of NIF was fired for that. Very, very low yields. But as you can see, we started getting better and better and better, got into burning plasma. And then August of 2021, I would say the world changed, and it finally went. It does not technically meet the criterion put out by the National Academies of Science, which for historic reasons told Livermore that they had to get more energy out than the laser put in. However, because this is indirect drive, that's not the correct way to measure it physics-wise, which is why in the laser fusion community, we say NIF did it, because it has all the correct physics parameters. So 2 megajoules of laser goes into that little gold box that I showed you, but only about 100 kilojoules of energy actually ablates the target. So to get 1.3 megajoules out for 100 kilojoules in, that would be ignition. They are struggling to repeat, but it is very exciting that they even got one, and hopefully it will motivate more good work in the future and better understanding as to how to repeat this. We'd like to do this every shot for both science and maybe future energy reasons. So the big question, because it's all neat science, but why do we care? What can we do with it beyond the national security stuff? There's inertial fusion energy, which is the thing that we're now trying to sell everyone on potentially funding. The Biden administration has shown a lot of interest in this. There's now money flowing for research. And maybe someday in the next 20 years, we'll get an EBR2 of fusion. The idea here is that we could use modern efficient lasers. So NIF is only 0.5% electrically efficient. We can get 15% or better with modern lasers. And then we will mass produce these little targets, drop them in and shoot them as fast as we possibly can, heat up a working fluid, boil water, and make power. From a fusion perspective, it has a couple advantages over some of the other fusion options out there. And that's that the most expensive part, the lasers, are very far away from all the radiation. And if you know anything about the fusion radiation environment, or remember what I said at the beginning, we're talking tens to hundreds of times worse than fission. So putting your really expensive components very far away is really nice for making them live a long time. Refueling also makes the pulsed operation also makes the overall operation a lot easier, because we can drop fuel in and then pull exhaust out just like your car engine does. And we don't have to have really complicated, if you ever see tokamaks or any of the other magnetic things, they're very complicated on the inside. There's a lot of flowing components that will need to happen. We don't need that for ICF. It's basically a glorified fusion diesel engine, if you can make it work. There's private companies getting into this game too. We have First Light trying to do gun fusion, just related, same sort of physics, but they're trying to use a super fast rail gun. There's a group trying to pursue that same sort of Sandia Z-pinch. A group out of Texas going for a version of laser fusion. I'm showing here. All very exciting. Lots of money flowing around. Maybe something exciting will happen. And then really long term, we could potentially use this for propulsion. That was actually the original idea of ICF, was to try to make gigantic fusion rockets to go between the stars. And there's some advantages here in that fusion would really struggle to compete in, or could struggle to compete in, the terrestrial energy market, but space is different. Space, you care about the total capability of whatever you're doing over everything else. So the fact that fusion can provide the most specific impulse, which is a measure of kind of efficiency of your rocket, even over fission, could make it competitive way in the future, probably when I'm long dead. So sorry, that was a whole gigantic info dump. Any questions, anything you want me to go back over?
That was awesome. How long does it take to set up one of these shots? What goes into that?
So at the facility I'm at, because we kind of have two advantages. We're smaller, but we're also older. We just kind of been running longer. We can do a shot about every 45 minutes. Our number one limit at this point is actually cooling of the lasers, which is something that could easily be engineered away. We just never thought we would hit that limit. We always thought there would be too many other things slowing us down. The next gen facilities that are being planned, we're talking about doing a shot maybe every minute. The lasers can be shot. It's been shown before that lasers can actually be shot faster than once per second. The question is going to be getting targets and getting the targets in. And then from a science perspective, we actually just can't take data that fast. So like for a lot of the stuff I do, I quite literally use film, and it just takes time to physically pull out film and put new film in.
How do you get data from this? I was thinking, how do you even measure how many, megajoules something put out? Like what's the instrumentation?
Yeah, the primary instrumentation is neutronics, as you would imagine. You just read the neutrons coming out. We have scintillator-based neutron detectors, like, are pretty typical, but the actual hard number, like when you say how much came out of anything, it's activation analysis. So you take a little block of some sort of metal. We typically use copper because it's got a good cross section for those 14 MeV neutrons, and then you pull that thing out and put it under a high purity germanium detector and count it. As a fun little side note there, NIF did not expect that gigantic fusion shot. It was a complete surprise. They were expecting to get something like 10 times less fusion yield than that. And they have armor that had been built way back in the day, boron carbide armor, that they can bring in to protect components. And there's certain things they have to do to prep the facility if they thought they were going to do that. Because none of it was ready, the entire facility was so activated, no one could go in there for like 4 days, and it knocked all the lights out. And some of their detectors were actually permanently damaged.
Were they able to explain yet, or they're still trying to figure out why it was 10x what they thought it would be?
That is, so there's the official explanation from NIF, and if you're in the room, you'll get 10 different explanations. The official explanation is they just kind of tuned it perfectly right, and they got the whole ROM was the right size compared to the capsule and blah 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 blah. But I've heard 100 different explanations as to what did it. The real crux of the matter is, because Congress kind of wheedled them down to less laser energy than they wanted, we all kind of thought they would be right on the edge at all times. And so you can imagine, it's like when you're trying to start your car, and sometimes it'll catch and sometimes it won't. I think they're perpetually at that point, and it would take a bit more laser energy, and then they would probably always do it. Now, of course, if we can always do it while being right at that point, that's even more impressive. But
how is Congress limiting the amount of energy?
I'm sorry, when they built the facility, they originally asked for 10 megajoules, and Congress said, we'll give you 2 megajoules, but it didn't even end up being 2 megajoules. They were funded, the way they were funded, they get about 1.8 megajoules of laser energy.
So would 10 megajoules been what? 10 times
prob-
cost or no? 5 times?
Yeah, it's not clear. I mean, NIF was such a leap in laser size. It kind of made sense to go for something that wasn't necessarily unbelievably huge. The next closest laser in size to it, the previous laser before it, was something like I think it was 75 kilojoules. So to ask for 10 megajoules from 75 kilojoules, I can see why there's some concern there. Nowadays, I think that would be the obvious move, would be to build the 10 megajoule facility, because we now understand how to build like lasers were very, very expensive back then. The prices have dropped precipitously in the past 20 years, and we've just gotten a lot better at it. And I would bet quite a bit of money if you built a 10 megajoule facility, it would probably just light every time you put fuel in there.
Wow. Is it powered by the grid then? They just,
The California grid. So
oh,
maybe they should put the next facility somewhere else for a bit more reliability.
yeah, no doubt.
Also, the sheer amount of tritium and activation and things like that, that's kind of the next step. Now that fusion reactors are finally starting to get to the point where there's interesting amounts of energy being made, it's time for the plasma physicists to meet with the nuclear engineers and discuss how do you make a real facility, rather than just kind of hand waving those problems away. We're talking about like 0.5 kilogram of tritium on hand for a power plant. It's quite a bit of activity. Tritium bioaccumulates, so you have to there's special rules on it, even if it's not very dangerous in all reality. It's just the NRC regulations are tricky. And then activation is just a problem. Fusion reactors will get very, very, very hot when during radioactively hot during operation. And so I've said in a lot of meetings, I think the next big facility should be put in Idaho or Tennessee, just to be near the people that actually know how to do it.
That would make sense. So what do you say if someone says something like, well, fusion's great because, there's no nuclear waste. We don't have to worry about the radioactivity.
I have to stop laughing first and then bring up, that, yeah, it's complicated, right? And I think specifically a thing I've been advocating for in the fusion space, and I'll point out that you all, Eric, you specifically have been brought up at fusion meetings. There's been discussion of like the fusion community needs to be proactive and not suffer the problems that the fission community had, and try to engage openly. And so a big problem I think we've been having is that there's a lot of people that will stretch the truth, a lot of experts specifically. And I think we need to come out openly and say, yeah, there will be radioactive waste. A fusion reactor upon shutdown will be actually equally as hot as a shutdown fission reactor of the same size. It will decay faster, but it will be different things that we have to handle. And we're going to have to be able to handle radioactive waste no matter what. The fusion reactor is also, due to how hot it is in the environment, in the specific environment, we're talking about only being able to do robotic maintenance, which is really tricky. No one knows how to actually do it. It's just always thrown as the next problem for the future. But there's a lot to still be handled there, and I think being extremely open about it is the only way it will ever get public buy-in.
Mm-hmm.
And I really liked what I heard at the last. So there's this gigantic plasma physics meeting every year in October, and I really liked what I heard at the last one, where there's a lot of talk about fusion energy. And one of the biggest things pointed out was everyone needs to stop bashing fission. It will not win any friends. And it will bite us all in the ass, because the Greenpeace groups are not stupid. They also can read the reports on fusion reactors and say, wait a second, you're all liars. So Larissa, I saw your question. There's no way for the facility to run away, I guess, is the most important thing to point out, especially with a laser fusion facility. the stored energy in the capacitors that power the lasers could potentially get out. You could have a failure of the pulse power system. If you've ever seen like a transformer bank go up, it would be like that. That is all very far away from all the radioactive equipment. So that's definitely, you know, those sorts of industrial accidents. There's always laser safety issues. Like lasers are really, I've worked with particle accelerators, nuclear reactors, and lasers. I will be honest, lasers freak me out more than the other two because I don't want to go blind. And it's very easy to have bad reflections. But yeah, beyond that, every fusion facility, laser or otherwise, will have to have an on-site reprocessing to make all that, to handle all that tritium with lots of liquid lithium. And so I would say that probably the most likely accident we'll end up seeing from fusion is there's going to be some sort of large tritium release from some facility. They're gonna fumble something because tritium really likes to get out.
And it's pretty
Thank
difficult to
you.
separate it from water, right? Like you need like isotopic separation.
Yeah, exactly. We actually store it as in uranium hydride of all weird things. Because the facility I'm at is one of the largest tritium holders on the planet. That's what makes us unique one of the things that makes us unique as a fusion facility. Most fusion research facilities do not do tritium experiments, and we do lots of them. There's, I think, actually one happening today. There's usually one every 2 weeks. And we're only limited by the NRC, actually. We could do more if we were allowed. Let's see, Doug. So in terms of material, there's not going to be any fission fragments, I guess, if that's what you're asking. There will be a lot of radioactive activated components. Fusion reactors will, on average, activate far more material than a fission reactor because most of the activity in a fission reactor is in the core, right? And then if we imagine a PWR, you have the core and you have the equipment holding the core and moving rods. Then you have a lot of water, and then you have the actual steel pressure vessel. The steel is being shielded by the water and never gets all that hot. Whereas a fusion reactor has none of that. So all sorts of stuff ends up getting quite hot. And we have to have certain materials in there that are arguably worse for activation. The worst question ever. What is your prediction for when fusion would be commercially viable to generate power? Yeah, thanks, Eric. I go back and forth on this. I think the really optimistic boosters are smoking some really strong stuff, and I'd like them to share. There's a lot of challenges left to get fusion, even to get just a reliable power plant running. And then from reliable power plant to economically viable is quite a step. I hope to see one before I die, but I think fusion is going to have a similar sort of development life as to say the fast reactor, where we can make one, and we can make one that operates kind of good at a national lab, and it will take a lot more to get it over the hump into the commercial space, because there's a lot of other things that you have to consider commercially that you don't care about when you're just making, say, a prototype power plant. So like, for instance, I think one thing that we're going to struggle with fusion, you'll always see people assume similar capacity factors to fission. And I think that's going to be really hard to hit, because fission got to that number by learning, by doing, right? They built power plants and they learned how to do better. Everyone in fusion just assumes we can do it. And we don't know where these things fail, because none of us have ever ran any of these machines long enough to discover. Maybe after the 10,000th laser shot, all the glass shatters or something. We don't know. Well, thank you so much for letting me rant at you guys for the last hour.
Yeah, this has been great. Very educational. At times I even like struggled to try to keep up with this. So I'm glad we can share this with the group, and I'm wondering if you might be able to like share a link to the slides or like a PDF or something of the slides? Is there anything else?
Yeah,
anything on here?
I'll convert them into a PDF and I'll send them to you.
Awesome. I always have this, whenever I think about lasers, I always am reminded of this back in Super Bowl 52, Tom Brady, Patriots versus the Eagles. There was some Eagles fans on the end zone shining lasers in Tom Brady's face, trying to distract him. So like, and they weren't strong enough to make a difference, but obviously this would be much further beyond that.
Yeah, yeah.
Melt Tom Brady's face off.
You wouldn't have a Tom Brady anymore if he ran into one of these lasers.
So, okay, so the one thing, so when you're talking about, is it viable as far as like the energy going in versus the energy get out? Is what you're talking about is the energy that the lasers are using to shoot into that fuel versus when the fuel fuses, I guess you could say, how much is released from that reaction?
Yeah, so there's two ways of talking about that. There's the term ignition, which I talked about in the beginning, where it's the energy that goes into heating the fuel. So there's, when you imagine like the laser, right? We have the electricity that goes into the laser, but then the laser isn't perfectly efficient. And then the laser isn't perfectly efficient at heating. So when you're just trying to talk about the scientific term ignition, it's just energy heating versus energy out. However, for an actual viable power plant, we of course have to go way above it. We have to make far more energy than went into the entire facility. And there's things beyond just, say, the lasers or the magnets or the whatever you're using, right? There's cooling systems for the fuel. There's, processing, all sorts of pumps, all sorts of other stuff. We call it circulating power. And you'll see this in a fission plant too. They have circulating power. They have a couple megawatts in the pumps, right? However, in fusion's case, we're talking about a lot more than a couple megawatts in some cases. And so we want to lower that circulating power, or at least differentiate the ratio as much as possible. And I think actually John here has a great point. This is the other thing that I constantly think about with fusion is that, it's got all the same problems as a fission reactor, but it's way harder. It's, you're running it with PhDs and you're using the most complicated equipment on the planet. And yeah, I sometimes think, John, that maybe the only viable path for a fusion power plant is some sort of 10 gigawatt scale monster, because there is some argument to be made with the way fusion has shown to scale that it might be economically competitive. Of course, where do you get your loan for a $50 billion 10 gigawatt power plant? I don't know. And we have to show it at a smaller scale, right? No one's gonna let me build a prototype 10 gigawatt plant. I have to show it at a much smaller scale that it's at all workable.
Ask Elon Musk.
Musk does not like fusion. He is not a fan.
You're kidding.
He has interacted with some people from our lab before as well, and we don't have a great working relationship with him.
What is it that he doesn't like about it?
He doesn't like things that don't work easily, is what it really comes down to. For all the difficulty of rocket science, it does not compare to fusion. You can build a rocket pretty quickly and start seeing results. Fusion's a little bit trickier.
Thanks, Gerrit. Really appreciate you doing this. And then send me an email with the slides if you can.
Yeah, I just did.
Oh, awesome. All right. Thanks, everybody.
Thanks,